Okay, let's start. Hello, everybody. Can you hear me well? Okay, how are you doing? Is all right? Okay, yes, we can hear you. That's fine. Okay, so today we are in week 11, and the topic is recommender system. And this is false written, but this is this notebook that I will cover. Okay. So you already saw during the class that recommender system basically is the aim of it is to predict the rating, for instance, of the movies. We will see this in the lab. They are very widely used on the internet, Amazon, YouTube, the video recommender system, for instance. And yes, in this lab we will see, first of all, how to do it from scratch. So we will build our own functions to compute the similarity, to create the neighborhoods, and to predict the rating of movies. And then we will see how to do it using the surprise library. Basically, this will be instead of like 100 or 200 lines in this case, this will be like 10 lines. We will see this. Okay. Okay, so we use the movie lens. This is a movie data set, and we will import it not as always. We download it in this case using wget, and then we unzip the file. That's the first step. So let's do it. So we download. This is to install the, if you don't have it, the package. Then we go to the directory data and we import the package, and we read the file name from this. So we directly download it from the internet, and then we unzip it. Okay, so we have some data sets .csv, some CSV files, and basically we will see later the links, the movies, and the ratings data sets. But first of all, we import the required packages. So Panda and NumPy. We will use this to manage huge matrices. You saw during the class that we have like this matrix with the users and the items. This is a big matrix, so we will use this package from SciPy to manage it. Then some function from SciPy to do a bit of linear algebra, sorry. Then, as always, to plot matplotlib, and then I have some formatting options, for instance, for Panda, that we only want 20 items to be displayed. Okay, let's run this. And also let's read the files. So we use the ratings, the movies, and the links data, and I also display it using this. So how does the data look like? We have this is the ratings row data. So we have a user ID. We have it's written here. We have like 138,000 users, and we also have movie IDs and the rating, the corresponding rating of the user for the movie. And we have around 27,000 movies. And we also have a timestamp, but it is not so useful in this case. And the second data frame that we have is the movies. So we have the movie ID, which corresponds to this one. Then the title of the movie. So Toy Story, very well-known movie, for instance, and also the genre of the movie. So if it's comedy, adventure, fantasy, something like this. And the third data set will be useful to to show the covers of the movies. We will see this. This is a sort of translation of the different IDs. So the movie ID that we use here correspond to an ID, official IDs, EMDB and TMDB ID, and this will be useful to get the cover from the internet. We will see this later. Okay, so that's it. And as an example, we have the movie Jurassic Park, which has the ID 480, and you can also see the germs of the movie. Okay. Any questions so far? Okay. I think it's all right. So if there is no question, let's visualize a bit the data. So we use this package, TMDB simple. Basically what it does it get the covers from the internet of the movies. So yeah, the covers. So we install it. In the case you don't have it, I already have it. And then I directly import a module from the GitHub page. If you see this, so I imported from HTTP import the GitHub repo, and then I import the week 11 package from the repository of the class. And what it does, basically, if I go to the repository, you will see that there is a file in week 11. There is this init.py file, and when importing the package, it runs this file. So basically, we have a class. So we import the TMDB simple package that we just installed, and this class is for retrieving the image poster, so the cover of the films of the movies, basically. So this is useful. We will see just now why. Yes, so we import directly like a model from GitHub that we created. So this may be useful if you want to use your own package and file library that you created, for instance. And what we do here is that we display the cover of the movies for the user. So we want the top 10 movies. So we sort the movies here. We sort the movies, and we take the top 10 movies of the user. So we specify the user ID, and then we display the movie, and we use this from the package. So week 11 TMDB, the TMDB class that I just showed you. We use it to get the URL, and then we display the covers of the movie. But let's see what it makes when executing this. So for instance, we want to see the movies of the user 6, and if I run this, there is no, because I didn't run this line. Of course, I forgot to run this. So it import the package, and then if I display the movies, we can see that user 6 watched 24 movies, and we see the top 10s based on the rating, based on its rating. So based on its rating, so this, if we go to the rating row, for instance, we can see that Toy Story is the first movie with the ID 1. If I go back, we can see that Toy Story has the movie ID 1 and is rated with 5. That's why it's the first, because the rating is between 1 and 5. So that's why it's the first in the list in this case, for instance. Okay. So we have a function to to display the covers, the movies of a particular user. And one important thing to remember also, we will see this afterward, but I already mentioned this, is that we will use an ID and an index. And in this case, this function uses the ID of the user. So we will see afterward what it does, what's the difference between ID and index. But we have to remember, and I also wrote them here, if you see this, that show movies for user uses the ID of the original ID and not the index. Okay. We also have some helper functions here. So one function to get the name from an ID. So you pass an ID, a movie ID, and you get the name of the movie. And also to display an histogram of the preferred genres of a user. And for instance, if we run this with the user with ID 6, we can see that he prefers comedy, romance, adventure, and he doesn't like children musical animation movies. Okay, and if I go to the functions, yes, so we print how many movies you watched. So this is the same. You select the user ID that corresponds. You take the ID, then you use the function, and you plot the genre. So you split, because the genres are like with this symbol. So you split the genres, and then you make a list of it, and then you count and you sort and you plot it. Okay. Any question on that? So for now, we have a function to show the movies, so the covers, and a function to show the preferred genres of a user. And both function, if you see this one also, this uses the original user ID and not the index that we will create in the next section. Okay, if there is no question, we can continue with a smaller data set, basically, because we had too much users and too much movies. So it would have taken too much time to run. So I basically truncate the data, and I only want like maximum 10,000 users and maximum 1,000 movies in my data set. So I just run this, and now we can pre-process the data. So we want, on the one hand, so we have on the one hand this ID, and we want to build an index that is consecutive, because if we look at the ID, we will see that there are users that do not have there are numbers, so ID, for which there is no user. So for instance, 0, there is no user that has the ID. If I go back, the ID 0. So we create an index, a consecutive index. This will be useful because then we want to have for loops, and so we want a consecutive index. But let me show you in the example. This is maybe more this is maybe easier to understand. So I pre-process the data, and we have starting from 0, we have this rating matrix basically we create this ratings matrix. We see that we have around 10,000 users and around 1,000 movies with this amount of ratings. But what I wanted to say is that we have this user that starts from 0 and is consecutive. And we created basically two dictionary to convert both the movies and the users to ID to index and index to ID, and the same for the users. And if I can show you this, for instance, for the ID, for the index 0 to 39, I print the index and the ID, and we see that, for instance, in this case, so this is like a translation of index to ID, and in this case, we see, for instance, that index 0 is associated with ID 1. And we use this because there are, as I already mentioned, there are like ID for which there is nobody. For instance, there is nobody with ID 37, and this would have been a problem when computing, for instance, the similarity of all users, because we will use for loops, and if there are ID missing, then it's a problem. So we had to have an index that is consecutive from 0, for instance, in this case. So we have 35, and then the next one is 36. So this is consecutive, and in this case, the ID is not consecutive, 36 and 38. So we will use afterward the index to compute the similarity, to do the prediction of the rating, and so on and so forth. So this is important, and we have to remember. That's why I wrote here. I don't know if you can you see this? Can you see my note here? So for instance, this tree function use the original ID, so we will have to use the dictionary to translate basically it, and then the rest of the function computes pairwise similarities and so on and so forth. We'll use the index, and we will have to be careful about this. Okay, I hope it's clear. It is quite important to understand because you will have to do an exercise, and you don't have to be, so you have to be careful to not to be confused with this. Okay, and I can also describe the rating. So what we just created in this pre-processing phase. So what we have basically now is an index of user, an item, and a rating. We have such a matrix. So a user index, an item index, and a rating associated to what the user, or how the user liked the item. The item is a movie, of course. Okay, any question on this? Is it clear so far? I hope. Okay, yes, it is. Thank you for the feedback. It is sometimes a bit worried to speak and you don't know if it's clear or not. Okay, thanks for the feedback. Okay, so we described the data. What do we have is, this is not so interesting, but for instance, this part is not interesting, but this part is. For instance, for the first user, we have 20, so user with index 0, we have 21, he watched 21 movies, and his rating ranges from 3 to 4, so he's like average. There is no movie that he really loved and no movie that he really hated. And the average rating of this user is like 3.666. Okay. And so on and so forth for all users, for all around 10,000 users. Okay. what we do now is we transform in this section here, we transform this rating from above that you just created, this rating matrix, we will transform it in two forms using this SciPy sparse. Basically, we create sparse matrices because it will be useful for dot products after, because we will use it to, for instance, compute the similarity. And also, we will create another one that is useful to quickly access it. So to quickly test, for instance, whether a user rated a movie. So we create those two matrices. Sorry. So again, the first one. So these are both another version of the rating data frame. This one is optimized for dot products. So if you want to do product of two vectors, we will do it while computing user similarities, for instance. And the second one is useful to quickly test whether a user rated a movie, for instance. So we access it quickly, and so we do this here. And if I run this, for instance, if we go back, user with index 0 and the movie ID 534, the rating is, if we go here, the rating is 4. This is this line here. So this user 0 rated this item with a 4, and it exists because there are many items and user item pairs that does not exist. There are many films that you did not watch, for instance. So so there are many pairs that does not exist, and you can test this using this ERDOC matrix, for instance, and this also the ER matrix basically. So if I run this should give me 4 in both cases. So we accessed in the ER matrix, we use the so the user and the item, so the value is 4. So the check is, so we check this, and also with ERDOC, the value is 4. So that's great. And if we further want to test the shape, so the number of users and the number of items, then we can also verify this, and we see that we have our around 10,000 users and around 1,000 items with this amount of ratings. So that's basically fine. Okay, any questions so far? Okay, if there is no question, it's written the fun starts here. Okay, so let's see. Yes, I have here a code that computes the average rating of each user. Basically, this is this column here. So remember 36666 and then 423323 at the end. Exactly. So we basically, the mean is, the average is easy to compute. So we do the sum and then the count, and we divide the sum by the count. And you also have this thread in Stack Overflow Stack Overflow, sorry, that explain this in more detail. But basically we have the sum over the count, so this makes the average. And if I run this, we can see that we have this 36666 that we had, and this 4.2333 that we had in the describe, using the describe here function. So we are fine. Okay, and this will be useful to compute the similarities between users. What we will basically do now. Okay. We want to now compute the user-user similarity. To do this, we will use this formula that we have in the slide. So we have the dot product of the two users. So we want to compute the similarity between two users. Basically, if they liked the same movie, they will have a high similarity. The similarity is like between -1 and +1. So a high similarity will say that they watched and liked the same movies, and a low similarity will mean that they don't like the same movies, basically. So we have the dot product of the two vectors corresponding to the users divided by the product of the norms. And we do this. So here are some tricks that explain how to do this. For instance, if you want to access an item, only the item in a sparse matrix, we can use this .a.item, so to only access the item. So if you want to do, for instance, the dot product, u.v transpose, then we have to get the item using .a .item. Because there are sparse matrices. So we assess. So this is, for instance, the dot product of user 1 and user 2. So this is this you can read it on your own. This explains basically everything that appears in the function, in this function. So we have two arguments in this function. The first one is an index. The second one is also an index of another user. In this case, we use the index, not the IDs, because we are using this matrix. So we use the index, not the ID. And we do the formula dot product divided by the product of the norms. So we create a copy of the matrix of the user ID, then we compute. So we remove the mean. So basically, this is the dot product of the mean centered arrays, not only the arrays. So we remove the mean, and then use this u dot that I mentioned earlier. So the dot product, and then this a dot item to access the item, just as above. This is the numerator, so the above part of the division, and the denominator, as already said, is the product of the norms. And then the similarity is then the numerator over the denominator. Okay, so that is to compute pairwise user similarity. So how user U and user V are similar to each other. And if I check this, for instance, the similarity between user 2 and user 6 is equal to 0.03. So they are not so similar. And you can understand this as a coefficient, like the coefficient, correlation coefficient, basically. This is almost the same formula as a correlation coefficient. So one means they are linearly similar, and -1 they are not similar or correlated. Okay, there is something in the chat. Sorry, why do you use an index? Yes, we will see in the following that we will need to use for loop over the index, and we saw just above that using the ID, this won't work because there are IDs for which there is nobody. So for instance, if you would use the IDs to do this, there would be nobody for ID 37, and this won't work the for loop because you you want to do the follow-up over all IDs. So we that's why we created an index that is consecutive. So the index is from 0 is consecutive. There is no missing value. So if there is a missing ID, then the index is not affected. 35 and then 36. So that's the only reason why we use this. And that's also why we have, for both movies and users, we have those user to user index, user ID to user index, and user index to user ID that we have to use. And as mentioned earlier, we have those functions that use the ID and the functions that use the index. So we have to be careful about this. I hope it answered your question. Let me see. Okay, yes. That if we know that index 34 is a particular user, will we be able to find back again who that person ID is? Yes, I just explained. You have those dictionary that we did in the pre-processing part. We have those dictionary to convert user ID to consecutive index and vice versa. So we will be able to convert. Okay. We want next to have a function that computes the similarity of one user to all other users. And for this, we may use a follow-up like here. So we have the ID of the user. So in this case, the index, and for all other ID in range length of the data frame, we want to compute. We use the above mentioned function, above defined function, and then we store it in a data in an array, in an MP array. That's one way to do this, and I also have one way to do it faster. So basically, we use this normalize and this repeat, but this is not very important in this case. So basically, this function and this function returns the same, but this function is way faster because we access directly from the error copy. So we access directly the data, and in this case, we use a follow-up. So this takes more time. But basically, the aim is to compute the similarities of one user to all other users. And of course, we can do this time trick to compute the time to compare it of the two functions. And in this case, we compute the similarities of all user to user 2 in this case also, and then we want to compare the time and also print the similarity of user 6 to user 2, so the sixth value of this data of this array. And if I run this, we can see that this one takes much more time than this one, basically. And that the similarity will be the same as before. So we had similarity between user index 2 and index 6 is like this. And in this case, it's the same answer, so we are fine. And we can see the time. There is no, yeah, there is a big difference. This is called basically the curse of the dimensionality. So if you have for loops in Python, this may took very, very long to compute. If you have, for instance, for loops in other for loops, then it takes a lot of time. And in this case, you do like products, and it does everything like array. It does everything at the same time. So it takes a much smaller amount of time to compute. Okay. And of course, the shape of this UU array is equal to the number of user. And if we print this, we can see that, for instance, this is the similarity of user with index 2 to himself. So it's 1. And we can also have all other similarities. But what we are interested in, for instance, is the most similar user to user with index 2. So we have -2 because -1 is himself. So we take -2. And then we first, of course, we first sort it. And then we take the second last value, or the penultimate, because the last one is himself. So, and it gives us a user with index 1871. And the similarity between those two is equal to 0.4, around 0.4. And what is, of course, interesting to see is to compare the top 10 movies of those two users. So here, for instance, we use this converting function, because remember that the show movies for user is based on the ID and not on the index. So we use this one twice to convert it. And if we run those two, we can see the movies that they watched, and basically we can see that almost, I don't know how many, but this one, Jurassic Park, is also here. This one is also here. This one is also here. This one here. So maybe 4 or 5 they watched in common with a similarity of 0.4. So this is the most similar user, but the similarity can be also sometimes greater, like 0.8, 0.6. But in this case, so a similarity of 0.4. So we have like 5 or 4 among the top 10 movies of both users in common. So that's fine. Any question on this part? So basically, this is the first step to predicting the rating. We have now a way to compute similarities between -1 and 1. And if there is no question, let me continue with the second step to this objective to predict rating. We want to create a neighborhood. What does it mean? Basically, we want to, for a movie and a user, we want to have the K nearest neighbor. This means the K user, so K may be 5, or in this case, we have the default value of 5. We want to compute for instance, the 5 users that also watched the items, or watched the movies, and are with the highest similarity to the user. So we enter a user, a film, a movie, a number of neighbor that we want, and this is to specify if we want the absolute similarity or not. In this case, the default value is false, and it gives us, in this case, the K users that watched the ID and have the greatest similarity to user with this ID. There is something in the chat. Why is VID means another user? When do we precise it? Can you elaborate on your question? I don't understand it well. So you mean maybe here? this VID. Basically, in this case, this is only in the range. So it's like for E in range M, you take the similarity of E and the other user. And in this case, you have two index in this case, or ID. So you want to specify one user and the second one. So this is another user, one user and the other. And in this case, you only have one user because you compute the similarity of all other user. So the E in range length of number of user. Then you compute the similarity of all. Why the letters V and U? Because we are working with vectors, and this is like V and U are basic vector stuff. If you do math, then V and U are vectors. X and Y are variables, and A and B and C are constants. So this is how do you say? Convention only. So is it clear now? So the letters V and U are only convention. You may have used X and Y, or what do you want? U like user and V like vector, maybe. Okay, I think we can continue. So we were in the create neighborhood. The aim is to compute the K most similar user that also watched the item. And if I run this, so basically you have the you compute the similarities of the ID, all similarities. Then if you want to take the absolute similarity, then you take the absolute value. Then you sort it, and you want the decreasing similarity, so you reverse the order, and then you create the neighborhood. So you ignore yourself, you ignore the self, then you ignore the user that have not rated this ID, and then you compute the ID, and if you get the K, you break it. There is something in the chat. I lost the sound. Can you hear me? You can't hear me. I guess I had a problem. It was written on my screen like your connection is, yeah, I lagged. I'm not at home, basically. Okay. No, it's fine. Okay. Where should I restart? Maybe. Did you understand this? Okay, it's fine. Did you understand this this function? What we are doing here? Or should I re-explain? But I think the lag came afterwards, so, but I can do this again. So basically the aim here is to create a neighborhood. So we have a user, a number of neighbor, an item, and we want to have the K other user that also watched the movie and have the highest similarity with the user we specify. And if I run this, for instance, we can see that we have 4 users with index 2 and the movie Jurassic Park. So the movie with the ID, this ID, and we have to convert it. So we get the name, we have Jurassic Park, and then we create a user neighborhood. We use the user index 2 and the ID of the movie. So it's a bit difficult, but the ID of the movie 480. So this is Jurassic Park, and we see that what we basically saw earlier, that the neighbors are the are people that also watch the movie, so also watch Jurassic Park and have the highest similarity to user 2 in this case. And this is the user that we had earlier in the other example, because both, we also saw that both watched. So we saw that this is the most similar user to user 2 with this similarity, and we saw that they both watched the film. So this is logical that it came at first in this case. And this is also, yes, so this is the similarity. This is the same, of course. And if you want to, if you are interested in the journeys histogram of the two, and this one, in this case with the second one, so this one, this user, we can see that they have the same preferences basically. So we had user 2 with index 2 likes science fiction, adventure, and thriller, and user with the second highest similarity and also watched Jurassic Park, we can see this here, has this preferences, and we also have, for instance, science fiction, action, so the same preferences because the similarity is high, so high, almost 0.4 in this case. So we have now a function that gives us k neighbor that also watched a film and that have the highest similarity with a user we specify. Okay, any question on this? Okay, if there is no question, we can continue with the final step. We want to predict the rating, so we will use two versions of the formula that is also in the slides. The first one is this one, and the second one is here. The difference between the two is that we use in this case like the deviation, and we had done something with the mean, and then here we use only this this fraction of the similarity and the rating. So basically a weighted average of the rating divided by the length, or the norm of the rating. So you implement this here, and then you can predict the rating for a user. A movie, you have to specify, of course, the user, the movie, the number of neighbor you consider, and then if you use this version of the formula or this one, and then if you want to use this absolute similarity or not. This was the argument of this function, basically. This one is the same. So again, we want to predict a rating. So we specify a user, a movie, a number of neighbor to consider. And if you want to use this version of the formula or this one, and to compute the rating, and also if you want to consider absolute similarities or not. And this function is also based on the index and not on the ID, because we have her.doc and her. So we print some stuff. So whether the user has already rated the movie or not. Then we compute the neighbors and we do the function. We implement basically the function. So we have the average, because we have this term here, the average, and this term here. Basically, this is this one. So we compute the average, then we compute the fraction in this case, with deviation or not, with deviation or not, and we do the the fraction here, and then we print the results and we return the predicted rating. So basically only the implementation of this function. And of course the so the sum is over the neighbors. So this case is important if you want to use 5 or 50. So it will sum over 5 or 50. It will do the average of 5 or 50 neighbors. Okay. I hope it's clear. So basically we only implemented those functions with the code. And if you want to check this, we can, for instance, with a number of neighbors of 50, with absolute deviation and with absolute similarity, with deviation, sorry, and with absolute similarity, we can predict the rating of user index 6 for user for the movie with the index 8 with a number of neighbor equal to 50 and the other two parameters. And if we do this, we will end up with the same result as here, hopefully. No, I already know that it's the same result. So it has not rated the item, and the prediction for this, in this case, is a rating of 2.75. We can see that the average of user 6 is 3.8, and we have this offset. This is this fraction because we use the deviation, which is equal to this, and the sum of those two equals the predicted rating. So basically we have the average, and then we have something that is computed from the neighbors to adjust the prediction. So basically it's an average prediction that is adjusted with this neighborhood. Okay, and if we want, for instance, to predict the rating of user 2 for Jurassic Park, we already saw that user 2 already watched and rated this movie with a 5, I guess, if I remember well. Yes. So he already has rated so the ID was 480, but in this case this is the index, so I have to convert it with a 5. So Jurassic Park, and the prediction using 50 neighbors is 4.5, around 4.5. So we have, in this case, the average of the user is 4 something, and the offset based on the neighbors is 0.4, and the sum of the two gives us a prediction for this movie and this user of around 4.5. And we also have, for instance, the item, this line, we can see that user with index 2 rated item 157 with a 3. And if we compute the prediction based again on 50 neighbors, we have a predicted rating of so the film is Congo and of 2.5. So, and in this case we can see the offset is really high because the average is also high. So that's it. Any question on the way to use these functions and to predict rating and to show to display similarity, to show the covers and so on and so forth? Any question? Okay, let me just recap. So we had at the beginning like 3 functions. On the top, we had 3 functions. The first one was to show the movies for users, so that they are based on the ID, and also to show the genre histogram for the user, and also to get the name of a movie based on the ID. And then we had 4 functions to compute the predicted rating. So first of all, the similarity, and they are based on the index, similarity to all users, and the neighbors, and at the end the rating. And we had also those functions, those dictionary to convert ID into indexes and indices into IDs. This is important because now we are going to do the exercise, and you will have to recommend 5 movies to a user. So of course the user must not have already watched the movies. So you have to complete the code. The first step, we recall the data frame we are working with, and so you choose your index. Then you print the ID using the dictionary. Then you have to display the movies that the user already watched. So you want to use a function that is defined above with the covers. Then we want to show the histogram of the genres of the user, also a function that is above. And you also have to think, okay, should I use the index or the ID? And then what is most interesting, we want to, among the 50 first items in terms of index, which 5 would you recommend? And of course, the user should not have already watched the movie. You have to use these parameters, and in this case, I already wrote a bit of the code for you. So we want to create a dictionary where you have the movie and the rating among the first 50, and you have to specify a condition that the user should not have already watched the movie, and then to compute the rating of the movie for this user. And then you have your dictionary where you have all movies that among the 50 first, all movies that the user did not watch, and the rating, and then it's basically done. So you print it. I did it for you. I do it for you. You print it and you sort it, and then you get the name of the top 5 movies based on the rating. So we have, among the 50 first movies, we want to predict all ratings, then to sort it, and to recommend the top 5 to the user. And remember the condition that you have to add here, such that the user has not watched the movie. And if you want, there is a last question to show the covers of the movies, but this question is more difficult, so you may do it or not, and you will also get the participation point without it. Any question on the exercise to do? From Brian, doesn't it take a long time to compute 50 rows of movies? Because my code has been running for a while, and I'm only at the 20th. It shouldn't take so long. Maybe like 3 minutes to compute. I already did this. So for 50, that's why we only have 50, because if we had all movies, this would take too long. Basically, you only use this for loop in the range 50, then you predict the rating. Okay, Alexander Koisen says it took me 9 minutes. Okay, and if it takes more time, I mean this is the end of the exercise, so you can submit it to me like until tomorrow. So if you do the beginning, it's already fine. Okay, so let's break out the session, and you have like 50 minutes. It should be enough to basically start running this, and if it doesn't complete, you can send it to me afterwards in every case, so it's fine. Okay, so you have until like 30, 32, 33. Okay, let's break out session. There is something else in the, okay. So how many participants? Like this. So okay, you have until 4:33. Okay, and if you have questions, don't hesitate to raise your hand. I guess you can raise your hand in the Zoom. Okay, let's breakout session. Okay, I guess we can continue. How was the exercise? Easy, middle, difficult? Yeah, Pierre, I understand. Pierre says a few minutes more would have been welcome. I understand this, but we have to finish the we have to finish the lab, and there is a bit remaining. So, but yes, I also thought about like a few minutes more. But you have time until tomorrow to finish this, and you can also like do it in groups and yeah. Okay, so I'm looking forward to your answers. Okay, so we in the first part we saw how to predict ratings from scratch. So we build these 4 functions to predict the rating at the end. And now we will do basically the same, but using a library called Surprise. So you have the documentation. If you click here, you can do this basically. So you can read this if you want. And we basically do the same, but in fewer lines. So if, in the case you don't have it, you can install you install the package. I don't have it here, so yes, I have it. And then you import the KNN basic and the KNN with means. This is the two predicting function that we had. So based on the neighbor, the basic, and the one with the mean. We also want a data set from this library, and then some stuff for afterward that we won't cover today. Okay, let's run this, and we use again a movie data set. So if you want to see the data set, it's on Kaggle also. Okay, and if you click on the README, you can see that we have 100,000 ratings from 1 to 5 from 943 users, and this amount of movies and blah blah blah, some description of but basically almost the same data. And we load it from the data set comprised in the package, and then we build the train set. So we build the train set, and as we can see, then we have so you have to download it to click yes, down, and then we have this amount of movies which corresponds to the description, so we are fine, and this amount of users, 943. We define some options, for instance, that we want to use the person coefficient as for the similarity, which is basically the same as before, what's in the slide. So this mean-centered cosine similarity, and then we want to use this user-based. We want to do this user-based because we can also do this item-based. You see this in the class, but we want to do this user-based in this case. And we use then we create an instance of this class, of this function from the package. So basically this line makes everything that we created in the functions above. So we specify the number of neighbor, the minimum number of neighbor, and then the option. And this is to show a bit what it does, but in this case we don't want to show this. You can try this with true. You will see some printed stuffs on information about the algorithm, I guess. And then I run this, so I create the instance, and then I fit the model on the train set, and I compute the prediction for test sets. The test set is some pairs that are not in the training set. So movies and user that did not rate some movies. That's our test set in this case. So we train based on based on the available data, and we predict for all pairs that are not in the training set. So we predict for all movies and users that's for which the user did not watch the movie. So you understood. This takes a bit of time, and then I print some of the prediction. You will understand why I took this 10 and not the first 10. You will understand afterward. So this takes a bit of time to run. And yes, so basically the important remark to do here is that in less than 10 lines, we managed to do the same as in the first part. So yeah, you may always want to look for packages on GitHub, on the internet, because this makes the job instead of doing it from scratch yourself. If you have some project in Python or in any programming language, basically. But of course, you will need also to check the packages sometimes. Okay. Any questions so far while it's running? It shouldn't take so long, but my connection is worse than at home. Okay, and then basically the last step is to do the same as before. So we want to get a top N prediction for all users. This computes the top N predictions of all users. So we, in the predictions that we have here, so it's done. But in the predictions we have here, so this is all predictions for all users that not rated the movies. So this is a huge matrix, and then for the we want to compute the top. So we sort them, and then we only want the top 10 for each user, basically, and that's what we did here. But before, I want to show you something. For instance, I took those lines to show you that, for instance, user 196, the predicted rating is for the movie with ID 868 is 5. Just remember this, because we are going to look at the top prediction of this user, and we will see this 868 in this case. So that's the helper functions to show the top N, in this case 10 predictions of all users. And if we run this, so based on the predictions that we just computed just above, then we get an array of the top 10 of the top 10 prediction of all users. And if you want for this particular user, we see that in this case, so we have the same user as before, and we will see that the movie with this ID also it refits. Yeah, so this I have to cancel, and then I can run this. we see that, for instance, the first one is this, so the movie that I just mentioned with a rating of 5. So this is the top 10 movies for user 196, and this basically this goes in this matrix, in this list, and took the best prediction for each user. Okay, and of course, then if you want to recommend movies, then you can use this top 10 to recommend to top 10 movies for each user to recommend to them, because they are likely to love to like them because the predicted rating is high. And also, as we use the test sets, so we are sure that they did not watch already, have watched the movies. And the last thing we can do is to do the same as before, using this TMDB to get the covers of this user, the same. We take the same user, and then because we have here we have IDs and we don't know which films, which movies it is, so we want to know this. So we first print the recommended items using the helper, the first helper function, I guess. Yeah, so the read item names, and then we also want to show the cover if it's available. So let me run this, and we will see, for instance, that so we have our IDs, and we see, for instance, that the first one is like Hertz and Minds from 1996. So with this list is the same as just above, but now we have the recommendation for this user. So we have the names of the films, and then also the covers, which is nice to have. And sometimes we don't have, because it couldn't find a cover. And also the URL of the image on this. So we use for this TMDB index ID. Okay, so the covers of the recommended films. So yes, with a package, sorry, this is of course easier to do, but we can also do it without understanding it, and this is a risk in this case. So packages are very cool to use, but be careful. Maybe you have to understand what they do, and also to check, because sometimes packages from GitHub can contain mistakes. But in general, also accepted packages from official packages from Python are fine. And yeah, that's it for the official parts. You will find some stuffs below that I won't cover today on cross-validation using this package, also the precision and the recall score, and you want also to tune the hyperparameter. So this is also cross-validation. And also we use this model KNN, and there is another model SVD. I guess the professor mentioned this in class in the last session. This SVD, you may want to know what it does. So you can read these 3 sections on your own. So I won't cover them. So that's it for today, and that's it for me for this semester. This was the last time, the last lab session. I really enjoyed giving this class, giving this lab sessions. This was the first time for me. I hope you enjoyed it as well, and you also learned a bit of Python and classification regression stuffs. And I hope it was useful to you. And I would like to thank you for attending the lab sessions, and wish you all best luck for the exams. I know there is no exam for this class, but you have exams soon. And yes, it was really a pleasure. And yes, see you. Bye bye. I will stay like 10 minutes. If you have question, you can ask. But the official part is now over. Okay. Thank you very much, and have a nice evening. Bye bye.